today for me to introduce our seminar speaker, Professor Anton van der Waan. He's a professor at materials at UC Santa Barbara. And Professor van der Waan got his PhD at MIT and then did a postdoc also at MIT before he moved to start his academic career at University of Michigan. And then he's from University. And then he moved to UCSB in 2013. And Professor van der Waan has been focused a lot on the first principle, first principle statistic mechanics application to predict the thermodynamic and kinetic properties of alloys, ceramics, as well as semiconductor materials. If you look at his title today, it covers both crystallography and thermodynamic and kinetics. I think for the graduate student, this is your comprehensive exam. Professor van der Waan has won a lot of awards, including the TMS Hume Rosary, among others. And he has done a lot of elegant work, especially on the intercalation materials for battery materials. So without further ado, let's welcome Professor van der Waan.
Thank you. Thank you, Claire, for a very nice introduction. I'm very much enjoying my visit here in Boise. It's beautiful. Love the view of the mountains and beautiful building here. And a lot of exciting research, clearly. I'm going to talk about battery materials. And they're very nice in the sense that when you actually do measurements, when you actually use the battery material, you are, in a sense, actually measuring things like thermodynamic properties, and you're seeing kinetics in action, everything that we kind of learn in a first-year grad curriculum in material science. And let me just kind of get the schematic out of the way in case you don't know how a battery works. It has three components. So two electrodes, an anode and a cathode. They are electronically conducting materials separated by an electrolyte, which is electronically insulating, but allows cations of a particular type. In lithium batteries, it would be lithium plus ions to diffuse through them. And the anode typically is something like graphite, and the cathode is typically a transition metal oxide, if we're talking about a lithium-ion battery. And the lithium ions like to insert between these layers. So in this image right here, this is a transition metal oxide where the corner points are oxygen, and the center of these octahedra are all transition metal, like cobalt or manganese or nickel. And they form these layered sheets, like these 2D layered materials. And between these sheets is where the lithium likes to intercalate. And they really like this to be in this crystal structure. But in the charged state of a battery, what you do is you move the lithium ions from these layers and insert them between the graphite layers. And that way they have a higher free energy than in this state. And so there's this spontaneous chemical driving force for the lithium to want to move from the graphite to this transition metal oxide to lower its free energy. But they can't do it because there's this solid electrolyte in between it. And the only way they can do it is if you hook up the two materials with an external circuit to allow for the electrons to move through the external circuit. The lithium plus ions then move through the electrolyte, and then they can lower their free energy by intercalating in this transition metal oxide. And all this chemical energy that's built up and that gets released is converted through this external circuit in kind of a controlled, reversible way. So that's the schematics. And just to kind of illustrate the richness of the crystallography and the compounds, these are three examples of among many, many, many of the kinds of compounds that are being explored and actually are in current lithium-ion batteries as the cathodes. So layered materials like the one I just showed, lithium cobalt oxide is one example, lithium titanium sulfide, more complicated ones where you have mixtures of transition metals in these octahedra. This is a 2D kind of material. Spinel is a 3D. These are the chemistries that typically adopt this crystal structure. And then also 1D kind of crystal structures. This is lithium iron phosphate. It's kind of getting traction in the Tesla batteries. They have one-dimensional tunnels for the lithium ions. And so that when you insert and remove lithium, they go down those tunnels. You can pull them back out, create vacancies, so forth. And because of transition metal oxides, their electronic structure is very rich. So when you put lithium in, you're actually oxidizing or reducing the transition metals. And the transition metals by themselves are very strange and rich electronic structures. So the magnetism is important, charge ordering, redox reactions, even kind of structural distortions that might be induced by changes in oxidation states. Okay, so this is why these electrochemical cells are so fascinating from a fundamental point of view. So if instead of using graphite as your anode, you use metallic lithium as your anode, and then you use a material like one of those from the previous slide, so one of these, so they're lithium iron PO4. So this is just shorthand notation for all the other stuff that's in this compound. So this could be iron phosphate or cobalt oxide. So if this is the material we're interested in, if we put this in an electrochemical cell of this form, then you can show thermodynamically that the voltage that you measure, and this is the Nernst equation, is related to the lithium chemical potential in this compound minus the lithium chemical potential in the anode, which if it's just pure metallic lithium, so lithium foil, is just a constant. And so what that means is whenever you measure the voltage in a cell like this, what you're really measuring is the variation of the lithium chemical potential. So it's a direct way of measuring an intrinsic thermodynamic property that is often very abstract kind of quantity to understand. And in other situations, is something that you can't measure directly. You always have to measure it. You have to calculate it indirectly by measuring other properties. But in an electrochemical cell, what you're really measuring when you measure the voltage is the chemical potential of the cation that you're shuttling back and forth. And so the chemical potential itself is really the derivative of a Gibbs free energy. So what you're really measuring is the derivative of the Gibbs free energy. So if you integrate the voltage, you essentially can reconstruct the free energy of your material. So so when you're actually using your battery, you're actually measuring the voltage and the chemical potential of your elements. And this has interesting consequences. Because if let's say you have a free energy curve that looks something like this. So M could be something like iron phosphate, and then this is lithium iron phosphate, and this is the lithium composition axis. And I think most of you are probably able to read a free energy curve like that. You know that if you're somewhere between X1 and X2, this would be the free energy of a homogeneous mixture, but that's higher than a two-phase mixture, which has a free energy lying on this common tangent. So between X1 and X2, you want to phase separate. Right? And so a classic example of that is oil and water. It would have a free energy like this. If this were water and this were oil, and then this is a mixture of oil and water, its free energy would look something like that. And if you're somewhere over here, you get some microstructure that looks like this, where you have discrete droplets of one phase mixed in a phase of another one. And so these battery materials, they do the same thing when they have a free energy like this. When you're inserting lithium, you're going in from here in this direction, and you first form a solid solution, but then you have to go through this two-phase region, which means you have a two-phase reaction where you have a sharp interface separating one phase, let's say the alpha phase, from another phase, let's say the beta phase. So you get this two-phase reaction when you get a free energy that creates a miscibility gap like that. And because of the Nernst equation, you can see this directly in the voltage curve, because the Nernst equation tells you that the voltage is related to the chemical potential, which is equal to the slope. And when you're inside this two-phase region between X1 and X2, your slope is constant, and so you get a constant voltage, a plateau in the voltage. So whenever you see a voltage curve like this, where you get a plateau, you know something like this is happening in your cathode material. You're going through a two-phase reaction. And you can make that a little more complicated. So often you might have an intermediate phase that's stable. This happens when maybe the lithium ions and the vacancies order. And then in that case, you break this common tangent, you create two new common tangents. And so that translates in the voltage curve to two plateaus where you separate it by a step. And so just by inserting lithium and then removing it back and looking at the voltage curve, what you're really doing is you're kind of sweeping through the binary phase diagram. And by looking at the voltage, you can kind of already sketch out what this phase diagram is going to look like, because you have direct access to the chemical potential. So let's look at now that we have these tools, let's look at an actual voltage curve. So this is for lithium cobalt oxide. This was really the first cathode material that got the lithium-ion battery revolution started in the 90s. It has this layered crystal structure. This is the voltage curve. This is the way that the battery folks kind of measure the concentration. This is called capacity, but it's really proportional to the number of lithium in these sheets. And so here the axis is inverted. This is fully lithiated, looks like this. And then when we're moving in this direction, we're pulling out lithium and introducing vacancies. And you can see there's a lot of features in this voltage curve. So in the beginning, you see a plateau, and that means you get a two-phase reaction where you go from a fully lithiated to a partially lithiated phase with a lot of vacancies. And that happens in a two-phase reaction. And then you have a solid solution, a sloping region, where you just have disorder between lithium ions and vacancies. And then at 50%, so this is where half the lithium ions have been removed. In that case, in these layers, the lithium ions like to order in rows. So you get a row of lithium, row of vacancies. And this is the pattern that emerges in these layers. And that shows up as a little step, so a little kink in this voltage curve. And if you couple this with diffraction, so you can simultaneously do a diffraction XRD study of this, you see superlattice spots of this ordering showing up exactly where these kink shows up in the voltage. And then if you keep pulling out lithium, you get another one of these little kinks. And in this case, it actually stages. So you get, again, orders, but now along the z-axis. You get a filled layer, an empty layer, filled layer, empty layer, and so forth. So all these things are happening every time you charge and discharge. It's basically going through a phase diagram, a binary phase diagram, and a whole sequence of phase transitions are occurring every time you charge and discharge. And of course, in addition to actually undergoing these phase changes, you have to remove lithium. So you also have kinetic processes where you have to have long-range diffusion from the surface to the interior or from the interior to the surface to go through the electrolyte. There's also a lot of interesting mechanical issues. This is again the layered material, but now looking at the voltage curve for a variety of different chemistries. So these all adopt the same crystal structure. All we're doing is just kind of taking these sites, these transition metal sites, and alloying them either with cobalt, nickel, or a mixture of them. And you can see each of these, when you change the transition metal, their voltages all change. And that means the transition metal is affecting the types of phase transitions that occur when you insert and remove lithium ions. So you get kinks and plateaus at different compositions. And another interesting thing is the lattice parameters. They also change dramatically as you extract lithium from these materials. This here is measured from in situ diffraction. And this is the C lattice parameter, which is really the spacing between these sheets. And what you see is initially, when you pull lithium out, up to about 70% pulling at lithium out, this spacing doesn't change that much. I mean, it changes a little bit, but doesn't change that much. But then once you've taken out 70% of the lithium ions, the C lattice parameter collapses drastically. So there's a dramatic drop in the C lattice parameter. And the effect of that is quite drastic. What happens is when you're pulling lithium out, you're depleting the surface of lithium, and that means the surface is at a low composition, and its lattice parameter wants to be contracted, whereas the interior of the particle is still lagging behind. It's still at this lattice parameter. So you build up these large stresses, and then that causes kind of the equivalent of mud cracking, this fracturing where these sheets might cleave, and you create other kinds of cracks. And so that's a problem. And so in axial batteries, you typically kind of stop. You don't pull out all the lithium. So you lose this extra capacity because you want to be able to cycle as much lithium as you can because of these chemomechanical issues that happen at the high states of charge. So that's another kind of challenge to overcome, is to overcome these drastic shape changes that causes fracture. So what I've done here is kind of describe batteries at the meso, maybe the continuum length scale, in a way that we're kind of used to as material scientists, kind of using phenomenological descriptions. So in terms of free energies, in terms of kinetic descriptions like Fick's law of diffusion, or maybe theories of phase transformations like a Cahn-Hilliard kind of equation for a two-phase reaction. And those are very powerful descriptions at this macroscopic length scale. And they're very useful to kind of understand and even engineer these materials. And then that's one extreme length scale at which we can describe these battery materials. And then there's another extreme where we can go really to the atomic and electronic length scale, and that's the electronic structure level. And ultimately, what we want to be able to do is kind of link these extreme length scales, because this gives us fundamental insight. It gives us ability to predict things, and it allows us to understand things from the atomic level and the chemical level. And if we are able to connect the electronic structure all the way to this phenomenological level, we can get a much better understanding of our material and also potentially design materials more rationally and more efficiently. And so a lot of what we do in our group is to develop methods to link this electronic structure method all the way to the phenomenological descriptions. And a lot of that will rely on statistical mechanics, because these are all thermally activated processes. So temperatures is very important. Entropy is very important. And so with statistical mechanics, we can predict thermodynamic properties, kinetic properties like diffusion coefficients, and increasingly solid mechanics kind of properties. And so the starting point, without going into too many details, is a first principles method to tackle the electronic structure problem. The workhorse nowadays is density functional theory. There's some tack-ons to kind of improve it for more complicated systems like transition metal oxides. But I won't go into details. The only thing to take away from this is, if you know the coordinates, if you have a crystal structure, you know which atoms, you put them in position somewhere, and then you can calculate its fundamental properties. For example, the energy of this crystal structure, its charge density, so that gives you some sense of how the ions are bonded together, and other properties like elastic moduli and things like that. So very fundamental properties that we can calculate with density functional theory, but they're really 0 Kelvin kind of properties. What we also want is to be able to predict finite temperature properties. So for example, if we're interested in phase stability, either as a function of temperature or composition, we need free energies. And so to be able to connect the electronic structure to these free energies, well, for that we have to rely on statistical mechanics. And the key equation there in any statistical mechanics book is the partition function, which is essentially a sum of the exponent of minus the energy of all kinds of excitations that happen in a crystal, divided by kT. And if you were able to evaluate this partition function, then you can plug it into this very simple formula, and then you get your free energy. So conceptually, at least formally, it's very simple. And what we mean by these excitations are different electronic excitations. So if you have a crystal, you've got electrons in them. If it's, let's say, a semiconductor, an electron can go from the valence band to the conduction band. That's the type of excitation. So you'd count over all those possible excitations. Vibrational excitations, atoms are always vibrating back and forth. If you describe that quantum mechanically, that's also quantized. So you can count them. So there's vibrational excitations. You can sum over all of those. And then for batteries, really the most important one for these battery materials is configurational excitations. This basically arises from all the possible ways in these materials of arranging, let's say, lithium ions and vacancies. So when you pull the lithium ions out, you leave vacancies behind. There's all this disorder that's created. And that each kind of decoration of lithium ions and vacancies is a type of configurational excitation that we would sum over. So formally, and then we've got the energy. So for each of these excitations, we need the energy. And in principle, we'd need to calculate the energy using something like this, density functional theory, which is solving this differential equation, and which is computationally very intensive. So we really can't use this as much as we need to by orders of magnitude to evaluate something like this partition function. So to overcome this challenge of calculating these kinds of thermodynamic properties, starting from a first principles method, we need a way to be able to interpolate and extrapolate these expensive calculations. And the way we do that is with essentially surrogate modeling. Nowadays, people call this kind of machine learning or surrogate models. But really, this is essentially coming up with functional forms to interpolate expensive density functional theory calculations. And they're called surrogate models, or we can call them effective Hamiltonians, or generalized cluster expansions. And let me just illustrate it with this alloy cluster expansion as one of the examples. So it has a form like this, kind of a linear expansion. And the way this works is we want to know how the energy of an alloy depends on the way you decorate this alloy. So you've got this parent crystal structure, in this case, a 2D triangular lattice, and you have different ways of arranging orange and green atoms. If you have a green atom, you introduce these variables, occupation variables, which are +1 if the site is green, and -1 if it is orange. And so each site has one of these occupation variables. And then the energy of the crystal, depending on how these atoms are arranged, can be expanded as a polynomial expansion of these occupation variables where you've got pair interactions, so nearest neighbor, second nearest neighbor, third nearest neighbor, and so forth, triplet interactions, and so forth. And then you have these expansion coefficients. And this is something that we can fit to expensive DFT calculations. And this kind of an expansion can then be extrapolated to many, many more excitations that we could sample in something like a Monte Carlo method. So this is the kind of workhorse of interpolating and extrapolating expensive density functional theory calculations to calculate thermodynamic properties. And this is just the simplest one. You can also do for vibrations. In that case, the degrees of freedom are not +1s and -1s, but actually displacement vectors, and these atoms are vibrating back and forth. And then you can come up with an energy expression that describes how the energy of the crystal depends on the current state of all these vibrating atoms. Or you could have a spin cluster expansion, so a generalized Heisenberg model, because a lot of these crystals are magnetic, so you've got magnetic moments. That's another degree of freedom. And the energy of the crystal will then depend on the relative orientations of these magnetic moments. And if you have molecular crystals, you can do it in terms of molecular orientations. You can do something like this, where you have a similar kind of expansion, but now in terms, let's say, of quaternions, which is a kind of a way to keep track of the orientations of molecules. So these are all very useful and mathematically rigorous tools with which we can express the dependence of the energy of a crystal depending on different degrees of freedom. And in fact, this cluster expansion method, which is which was triggered by this original paper over here in 1984, this cluster expansion method is a very rigorous mathematical formalism to formulate and to express these cluster expansion Hamiltonians. It was recently extended to off-lattice kind of descriptions and shown that most of these machine-learned interatomic potentials that are now very popular are actually approximations of a generalized off-lattice cluster expansion following the same math. So a lot of this machine-learned interatomic potentials is really actually just rigorous math, but done in kind of an indirect way with fancy machine learning tools that are now available. But essentially, all these tools of extrapolating DFT methods can be formulated in terms of these cluster expansion techniques. So in our group, we developed a software package to automate the construction of these Hamiltonians. And very briefly, this is kind of a busy slide, but you kind of have a menu of different degrees of freedom. So you pick a crystal structure. If you're interested in alloying degrees of freedom, then you have chemical degrees of freedom. If you're interested in vibrational degrees of freedom, you pick the displacements. If you have magnetic, you spin degrees of freedom. And then what it does is it automates, spawns off, and enumerates different excitations, sends it off to a DFT method, for example, a VASP code or quantum espresso. And then simultaneously, it algorithmically constructs these Hamiltonians using group theory of symmetry to kind of clean it up. And then does some training of the expansion coefficients using the DFT data, and then sends that off to a Monte Carlo code that's tailored for this particular Hamiltonian. And from that, you can calculate a variety of thermodynamic and kinetic properties. And so this is a tool that's open source. It's now mostly in Python. We're trying to make it more and more user-friendly. So if you want to do one of these things, especially these simpler things, hopefully it should be easy to do by just downloading the code and kind of going through the steps. So what I want to do is just illustrate this for a few examples in the context of battery materials. And the first one I want to just illustrate, just focusing on these chemical degrees of freedom. So in a battery, when you take a host material, you remove lithium ions, you create vacancies. There's all this lithium vacancy disorder, and that leads to entropy, and that affects the thermodynamic properties like the voltage. So let me illustrate this for this example. This is this is already an old study, but this is TiS2 in the spinel crystal structure. And it's known that you can insert lithium and then remove lithium. And about 10 years ago, there was a lot of interest in looking at magnesium, replacing lithium with magnesium. So magnesium is 2+, so that means you can get more charge in and out per cation. So there's a lot of interest there. And so we wanted to see, okay, what if we, instead of putting lithium into this compound, insert magnesium, what kind of voltage curve would we get? And so we calculated the voltage curve using these techniques, only allowing for magnesium vacancy disorder. That's the only degrees of freedom that we considered. And we got this red curve over here. And you can see you can get a little more than 0.8 magnesium per titanium sulfide unit into this crystal structure. And then a year later, Linda Nazar's group actually was successful to experimentally realize this. So they made a cell and used this as the cathode, and they inserted magnesium, and they got this green curve over here. And you can see, so this was a prediction before the experiments were done. And you can see very good qualitative agreement and also very good quantitative agreement. Now, the quantitative agreement is because we're doing a sulfide density functional theory, which is the starting point, is very accurate for sulfides. But note, we've only considered magnesium vacancy disorder. We're not considering vibrations. We're not considering other excitations. And just by considering magnesium vacancy disorder, just the entropy of that, that's sufficient to essentially capture all the qualitative trends in this voltage curve as a function of the magnesium content. Now, what you can see is experimentally, we're only getting up to about 0.4, 0.5 magnesium into this compound. So, but our calculations indicate you should be able to get much more magnesium into this compound than 0.4. So that made us curious. And so the next few years later, we actually then went ahead and calculated the diffusion coefficients. So the magnesium diffusion coefficient. And this is what we predicted. So we get roughly constant diffusion coefficient up to about 0.4. And then once we hit this kind of composition, you can see the diffusion coefficient suddenly crashes out. So by almost 4 orders of magnitude. So essentially around this composition where the experiments were unable to get more magnesium in, the diffusion, the mobility of magnesium just shuts down and you're unable to kind of continue to diffuse magnesium in. So this is an example where the modeling helps us understand what the limitations are experimentally. And if I have time, I'll come back to exactly why this diffusion coefficient tanks out at that composition. There's interesting kind of crystallographic reasons for that. But before I do that, let me give you a few other examples of the kinds of things we can calculate with these tools. So let's look at something with magnetic degrees of freedom and maybe even couple it with chemical degrees of freedom. So this is a phase diagram. This is not a battery material, but it's something kind of similar. You've got, this is a Heusler compound, manganese, iron, ruthenium, and tin. And it's a Heusler compound where the ruthenium and the tin are kind of fixed, but you've got an FCC sublattice that you can alloy with either manganese or iron or a mixture of it. So this sublattice you can mix with manganese and iron, and so you can vary the composition of this Heusler phase by changing. If you start with the manganese over here, and then replacing manganese with iron, you can make it more and more iron rich. And this is the calculated phase diagram. So this is a temperature axis, composition axis. And it shows a miscibility gap and also magnetic transitions. So the the manganese-rich wants to be anti-ferromagnetic, so the magnetic moments are opposite spins, and this is an anti-ferromagnetic phase. Over here, this is a ferromagnetic phase. This is where it's iron-rich. In that case, all the magnetic moments want to be parallel to each other. And then they disorder over here to form a paramagnetic phase. And there's a miscibility gap, and then these magnetic transitions appear to come together at this tricritical point over here. Now, so this is where we combine chemical degrees of freedom and magnetic degrees of freedom. Now, these simulations were done in the Monte Carlo with assuming Ising statistics. So Ising statistics means the spins can only be up or down. There's only degrees of freedom. Heisenberg statistics allows the magnetic moments to be any continuous value. They can be any kind of continuous orientation. So there's many more degrees of freedom if you allow for Heisenberg statistics of your spin. And what you can see is, if you allow for Heisenberg statistics, the paramagnetic phase, which is a disordered arrangement of magnetic moments, is much more stable because when you have Heisenberg statistics, you have much more entropy because there's many more possible states of the magnetic moments. And so the Heisenberg statistics pushes these magnetic transitions to much lower temperatures. And when we actually do quantitative comparisons to experiment, we get excellent agreement if we compare these transition lines to actual experiments than if we do Ising statistics, which tells us that the physics of this material, the magnetic moments, are these continuous degrees of freedom. You have to really do the Heisenberg statistics to do the magnetism right. And it affects the rest of the topology of the phase diagram. It depresses this miscibility gap to much lower temperatures, which is a chemical miscibility gap. Very briefly, just to, for maybe if there's any folks that grow epitaxial phases or crystals or alloys, we've developed, we've extended these methods to allow for chemical degrees of freedom and strain degrees of freedom, which is important when you're epitaxially growing phases, because then the crystal that you're growing is under epitaxial strains, and that will alter all the thermodynamic properties. You can take what's otherwise a phase-separating alloy. If you grow it epitaxially, sometimes you can make it mixing or ordering, so you can drastically change the thermodynamics. And this is a very busy slide. I apologize for it, but this is just how to do strain rigorously. This is just the cluster expansion formalism when we allow for strain and chemical degrees of freedom. But the key takeaway are plots like this. This is a free energy curve of silicon germanium as a function of composition and as a function of strain. So you can formulate free energies that are functions of not only composition and temperature, but also explicitly as a function of strain. And that way you can then analyze, okay, if you strain it, how does that change the free energy, and so forth. And it allows you to go beyond nonlinear elasticity because the curvature is related to the elastic moduli, and this curvature is clearly not constant as you change composition or as you change strain state. So anyway, a new thing that we've recently developed. Okay, so let's come back to batteries and use these techniques to kind of explore different behaviors in ways that might be more difficult experimentally. So because when you do modeling, you have control over what you're actually doing. In experiments, often the chemistry and the thermodynamics doesn't let you do things as systematically as you might want to. So one thing we can do is we can take, let's say, this layered host material and systematically compare, okay, what happens if we, instead of putting lithium between these layers, put sodium, which is bigger. So this is the ionic radius of lithium, and that of sodium is bigger. So the size, we can independently look at the effect of size on how these intercalation compounds behave. Or we could, instead of lithium, we could put magnesium, which is 2+, but has roughly the same ionic radius. So this axis, we can explore the effect of oxidation state without changing the size. So we can kind of independently look at different effects. Well, if we insert lithium in this layered material, TiS2, we'll take TiS2 as kind of the model system. This is the voltage curve that we get, very smooth. Smooth voltage curves means just disorder. Here, there's a little plateau, means a two-phase region, and a little step, and that means it's staging. So it wants to have filled layers, empty layers, filled layers. That happens over here. But other than that, not much is happening. When you do magnesium, then you get a voltage curve like this. So here, you get all these little steps, and they're pretty pronounced. And each step corresponds to an ordering of magnesium and vacancies. And the reason these are so stable is because magnesium's 2+, so you have this very strong electrostatic interactions, much stronger than between lithium. So the in-plane interactions between magnesium are much stronger, and that leads to pronounced ordered phases at these stoichiometric compositions, like 1/6, where you have the stage phase, 1/3, or 1/2, where you get these rows. And each one translates into a voltage step. But it gets very interesting when you look at sodium. So if you put sodium between the same layered materials, sodium is bigger. And because it's bigger, it actually causes much more dramatic changes in the host compound as you're changing the sodium composition. So this notation here, this just reflects different stacking sequences of the TiS2 sheets. So these are TiS2 sheets, and then the yellow are the sodium ions. And in this O3 stacking, you have a particular stacking of these sheets such that the sites that sodium can fill are octahedrally coordinated. And that's why this is O. And then the P3, this is where the sheets have had to undergo a glide transition. So they glide, and that then shears the sites that sodium can reside in, and they become prismatic. So these are prismatic sites, and that's where the P comes from. And so what you see is, because sodium's bigger, when you start with this O3 stacking, you pull sodium out, you create vacancies, and then this stacking sequence becomes unstable. It wants to undergo a glide transition, and you form this prismatic stacking. And that's stable over this region. So you have a two-phase reaction to go from this stacking sequence to that stacking sequence. And then if you continue taking out sodium, you get staging, where you have mixtures of empty and then P sites and empty and so forth. And you get a sequence of other phases. And this is a very interesting, and it's very important as well to kind of be able to get battery materials to work. These glide transitions are very important in these sodium intercalation compounds. They occur all over the place. And this is very similar. So in O3, the oxygen sublattice is an FCC sublattice. So for those of you who are material scientists, you all know about FCC. And if you want to go from an FCC stacking sequence to, let's say, an HCP stacking sequence, that one way to do that is by passing partial dislocations through your crystal. So to undergo a stacking sequence, you have to pass dislocations through. So this is what's also happening here. When you go from this stacking sequence to this prismatic stacking sequence, you have to have partial dislocations that migrate through this crystal structure to realize this stacking sequence. And so at the particle level, one way you can do that is kind of crystallographically, you create these partial dislocations, and it's a kind of a complicated network, positive, negative, and some planes that are unaffected. And so you have all these little dislocations along this interface, separating P3 from O3, and these little dislocations have to migrate through the crystal as you're pulling sodium out to form the P3. So it's, instead of a mechanical deformation that's causing dislocations to move through the crystal, it's actually a chemical removal of atoms. It's a chemical driving force that causes dislocations to move through this crystal to realize this stacking sequence. So it's a very interesting chemomechanical problem that is still not really well understood. And there hasn't been much done experimentally to characterize this, because all this stuff happens dynamically. It's very difficult to kind of trap this type of structure. But there's a lot of fundamental science still to be developed and discovered there. But let me come back to, again, looking at the ordering tendencies within these structures. So the O3 and the P3. And it's very, very interesting. There's very interesting differences. So in the O3, if you look at the sodium layer, the sites that they can occupy form a triangular lattice. So that's the lattice in these layers. It's triangular. Whereas in this prismatic, in that case, the network of these prismatic sites, if you look at all of them together, they form a honeycomb network like this. So you have a different kind of network of sites for the sodium ions. And that leads to interesting ordering phenomena. So let's say we have this network like this. This is the P3 structure. You have this honeycomb network. And when you have sodium TiS2 in the P3 structure, every other site of the honeycomb network is filled. So you've got a filled, empty, and so forth. And when you pull sodium out, you're going to leave behind vacancies. And so normally in most of these battery materials, like O3 and lithium battery materials, you create vacancies, and they entropically spread out. They don't want to really cluster together, and they also repel each other energetically. So you have these, that's what you would normally expect. But on this honeycomb network, the topology of the network causes interesting things. This is something that you can calculate with DFT. So this is a periodic unit cell. So a structure like this, instead of having vacancies uniformly distributed, what it would rather do is have the vacancies coalesce at antiphase boundaries. So here, and then you have perfect ordering. So you don't have these isolated vacancies. Instead, you have all the vacancies coalesce at these antiphase boundaries, where you have perfect ordering. So it's filled, empty, empty. And normally you'd expect the filled one, but that's where the vacancy is. But instead of then continuing with empty, filled, now you form a perfect ordering also of sodium, but shifted to the other sublattice. So you kind of create an extended antiphase boundary. And here is another antiphase boundary of a different type, but it's the similar kind of concept. So you have these antiphase boundaries. And this is the type of supercells that you can calculate with DFT. That's what's reasonable. But when you map all those energies on a surrogate model, like a cluster expansion, and then go to Monte Carlo, you can look at the pattern formation at much larger length scales, and you're not restricted by these small periodic unit cells. And in that case, what you see is that the favorable antiphase boundary is actually this one, and there are 3 orientations, and that's why you have these 3 orientations over here. And so you get these kind of triangular networks or triangular patterns, kind of fractally patterns. And so this is a structure where you have a whole bunch of vacancies, and all the vacancies coalesce at these boundaries that separate perfectly ordered domains like this. And so as you remove sodium, so you start, this is a snapshot from one of the layers in a Monte Carlo cell of a big sodium TiS2 crystal. And this is at x equal to 1, all the sites are filled. And then you pull a few sodium out, so you leave some vacancies around. And instead of having randomly distributed vacancies, they all coalesce to form these, along these antiphase boundaries. You get this fractal-like pattern. And then you remove even more vacancies. And what you need to do then is, because you have more vacancies, you have to increase the total line length of these antiphase boundaries. And so that means you chop up these domains into smaller domains so that you increase the total line length, and you continue to do that. And so you have a very different form of creating entropy than that of just randomly distributing vacancies on a lattice. It's more of a kind of a fractal entropic kind of accommodation of these vacancies. So this is all, let me see how much time I have. 5 more minutes? Okay. This is all for sulfides. For oxides, oxides tend to be more ionic. So the interactions of the sodium ions are much stronger in these layers. And you can see that in the voltage curve as well. You get large steps and very complicated kind of structures in the voltage curve. This is calculated, and then this is experimental. With oxides, DFT also has a systematic error, and that leads to kind of a systematic shift in the predicted voltage. But you can see that the relative variation agrees very well with experiment. So the same phenomena are happening, it's just a constant offset. And with the oxides, it really likes this ordering at 50%. This is at half, and this just maximizes the separation of the sodium ions. And it likes it so much that if you try to disrupt it, it will again try to preserve it. So for example, that's why you have this big strong step. That's this ordering right here. But if you want to pull some sodium out, instead of just removing just a few sodiums randomly, again, it would much rather prefer to form an antiphase boundary where you have the same ordering but shifted, and then you have an antiphase boundary where you have less sodium. And that leads to these little steps in the voltage curve. And that's a much energetically much more favorable way of accommodating all these vacancies in this crystal structure. And you can do it on the other end as well. So you see this kind of staircase. And it's called a devil staircase, because you can always come up with more complicated patterns of these antiphase boundaries. Where in this case now you have excess sodium along the antiphase boundary. You preserve domains of perfect ordering, but then you kind of translate them on the honeycomb sublattice, and that gives you this antiphase boundary. And that's how you can accommodate differences in composition. So the way you change the composition is you maintain these perfect domains, but you just increase the frequency of these antiphase boundaries, and that way you can change the composition, right? You add more vacancies by introducing more antiphase boundaries over there, or you add more sodium by just increasing the density of these antiphase boundaries because they accommodate more of these sodiums. So that's what happens in the oxides. So it's even more pronounced and richer over there. And the reason that this is important, and unfortunately I probably won't be able to get to it, is, I mean, it's very interesting, but it actually has important consequences for diffusion. It turns out that the antiphase boundaries are actually crucial to mediate diffusion. And it's not the usual mechanism of atoms exchanging with vacancies in these sodium compounds. Instead, it's actually the motion of antiphase boundaries themselves that are going through the crystal. So the diffusion is not a vacancy mechanism, rather it's waves of these antiphase boundaries going through the crystal, and that's how you can accommodate composition changes. It turns out that the kinetics of moving these antiphase boundaries with a kink mechanism and extension is much more facile than moving individual sodium atoms by exchanging with vacancies. So very quickly, and then I'll kind of wrap it up. Diffusion, we can calculate that as well. The nice thing about diffusion coefficients is that you can use Kubo-Green type of expressions, which basically means that you can calculate diffusion coefficients, even though it's a non-equilibrium quantity. You can calculate it by tracking fluctuations that happen at equilibrium, because the fluctuations that happen at equilibrium are a measure of the mobility of atoms. And so there's these complicated expressions like this. The diffusion coefficient you can factor into kinetic factor and a thermodynamic factor. And so there's a chemical potential in the thermodynamic factor. And in this one, this is a kind of a quantity that you can calculate with kinetic Monte Carlo. And so the way that works is you have a bunch of sodium atoms or lithium ions in a crystal, let's say on a triangular lattice. And with kinetic Monte Carlo, you can sample different trajectories. You take the endpoints after a certain time. These delta R's are the endpoints of those trajectories. You sum them up, you square it, you divide by the number of lithium ions, you divide by the time of the simulation, and that gives you a measure of the diffusion coefficient. And what you're really keeping track of is the geometric center of mass of these atoms that are in equilibrium, but they're always fluctuating and diffusing around. And that gives you this thing. And so you can calculate the diffusion coefficient. You can construct kinetic Monte Carlo with transition state theory for the individual hops. But the problem with these individual hops is that in a disordered system, like a battery material, these barriers are going to depend on the local environment. So depending on where you are, this barrier will be different. And so again, you have to use these cluster expansion techniques to parameterize the dependence of these barriers on the local environment. And then you can go to kinetic Monte Carlo and calculate diffusion coefficients. And so I'll end with this, but this is just calculated diffusion coefficients. One is for a layered material. The other one's for the spinel compound for lithium. The exact same chemistry, TiS2, just a different crystal structure, vastly different diffusion coefficients as a function of composition. First of all, the diffusion coefficients change dramatically with composition by many orders of magnitude. A lot of that has to do with dimensional changes of the crystal, so lattice parameter variations as you change the lithium composition, but also at higher compositions, because in the layered materials, diffusion is mediated by die vacancies, whereas in this spinel, it's mediated by triple vacancies, and those kind of start running out at high composition. I did say this was my last slide, but I think the next one is just to illustrate, this is a very inefficient mechanism of diffusion with these die vacancies. And so that's why the diffusion coefficients have such a strong composition dependence at high composition. So I'll end there. Thank you very much for your attention.
So any questions for Professor Vanderwall?
Great talk, thank you. So you had a slide about the P3s, I think sodium titanium sulfide. And you showed this mechanism of the P3O3 transformation by the formation of dislocations. So in a lot of the other like layered materials, we talk about like the layers gliding relative to each other to create the O3 to P3 transformation. So can you like compare the relative energy of those two different mechanisms, either just gliding of the whole layer without any dislocation formation compared to?
Well, I mean, this, if you take a crystal and you try to mechanically deform it, you can't glide the whole layer because the energy scales with the whole area, right? So it's kind of like moving the rug through the little dimple in the rug through, right?
Yeah.
Like we all learn in the beginning in material science. So it's the exact same arguments. So in these materials, the layer won't glide instantaneously. It has to be kind of a phase front that moves, but the interface is really a partial dislocation. That's the hypothesis, and we need experimentalists to see it.
So just short follow-up, do you think that would change between like the sulfides and the oxides, like but the relative
I think
energy
so,
of those?
Yeah, because the sulfides are probably are less stiff, maybe less inclined to fracture as you pass this dislocation through than the oxides.
Thank you.
Graphite does the same thing, but the graphite does not, and we do. So graphite, when you stage, you also undergo a glide transition, And presumably that's also a dislocation, but that is happening in every single one of your little devices right now. So in graphite, it is feasible to do it. But in these sodium intercalation compounds, there's still issues that we need to overcome to make it feasible.
Yeah, I have I think a similar question. It may be the same. I'm ignorant of battery materials, so thank you for your talk. This has to do with the sodium titanium disulfide devil's structure. I think you were talking about FCC to prismatic or HCP.
Yeah.
Mediated by partial dislocation, driven by a chemical potential gradient.
Right.
So when I'm thinking of partial dislocations, and I'm pretty limited there, but it was silicon germanium type work.
Yeah.
I think stacking faults.
Yeah.
Are stacking faults present then?
Well, this is if you're doing this layer by layer, you're creating a stacking fault.
A stacking fault.
And
okay.
then if you do it every layer, once you've created a stacking fault in every layer, you've created a new crystal, right?
Right.
Right.
Okay. So okay.
Yeah, yeah.
Thanks.
So it's the same idea as right.
Okay. Any other questions?
Thank you for the talk. My question is, in your modeling of anharmonic vibrational cluster expansion, are you able to account for localized changes in displacement as the redox state changes?
Yeah, in principle you could. Yeah, right. And this is important for Jahn-Teller distortions. So, or even in your case with the titanium, the second order Jahn-Teller distortions. So so you will have a Hamiltonian that describes kind of the resistance and the tendency to form a spontaneous distortion of the octahedron. And the parameters that describe that are going to be dependent on the oxidation state. So if the oxidation state changes, then suddenly there's an instability and it will want to pop into Jahn-Teller distorted phase. Yeah.
Thank you.
Any more questions from the audience?
Great talk. This question's more general about how batteries work. So in general, you have like the lithium atoms getting like inserted into the ordering of the structure and getting removed from the order of the structure to transfer energy. Is it possible to have a crystal set up where the anions are what's getting removed and entered into the structure to transfer energy?
Yes, you could do that. Yeah. To some extent, solid oxide fuel cells are like that, where the electrolyte transports oxygen anions. And so if you have on one end air as your anode, let's say, and you have any metal that reacts with oxygen, that would be a battery. And if you look at titanium, zirconium, hafnium, they actually, they have a HCP crystal structure, and they're remarkable in the sense that you can intercalate oxygen in that HCP crystal structure, just like these layered battery materials, and fill up half the octahedral sites in the HCP crystal structure with oxygen before it forms other oxides. So in principle, you can make a battery out of, let's say, zirconium, a solid oxide fuel cell electrolyte, and then some air, and hook it up. But you'd have to do it at high temperature because the kinetics are much more sluggish.
All right, thank you.
Yeah.
Any more questions? Oh. We have a lot of questions.
Hi, I don't know anything about batteries either, but I love the thermo and kinetics. So, I was just curious. You had shown some of the particles as they're being discharged and the ions are being removed. They develop tensile stresses at the edges and so forth. I'm just curious how you've looked at the influence of strain on the diffusion kinetics.
It's huge. It's huge, and that's why in this picture right here, that's why the diffusion coefficient drops by orders of magnitude. What's happening here? Remember that plot I showed you with the C lattice parameter? This is for a layered material. So remember, the C lattice parameter is more or less constant up to here, and then it starts to drop just like this diffusion coefficient. So what that means is when the C lattice parameter drops, this interlayer spacing decreases, And this site, which is where the lithium hops through when it goes from one octahedral site to another one, this one gets crunched down much more rapidly than the initial site. And so the migration barrier increases by 100, 200, maybe even 300 MeV. So it's an enormous effect.
Thank you, Dr. van der Veen, for this beautiful talk. When I hear batteries, I think less about materials. I think a lot about cobalt that we get out of the Democratic Republic of the Congo, and which is going into all of our batteries. And so when we listen to your talk and what you do here, do you get from this work strategies how to power our electric vehicles by less importing cobalt out of the Democratic Republic of the Congo?
Yeah, well, Claire is definitely working hard at that. The obvious replacements are things like nickel, manganese. And nickel is more, so cobalt works beautifully. Electronic conductivity is great, diffusion and so forth. Nickel has its own issues because you can't make it without extra nickel in the layer. So there's always some nickel stuck here, and that causes problems. And then the manganese, that one is also a problem because manganese, contrary to cobalt and nickel, manganese is able to become 2+ in some circumstances, and then it's very mobile and it diffuses down and kind of moves all over the place, and the material destroys. So there are obvious replacements, but they have all these other issues. And so these modeling tools help us understand why they don't work, but the options are a little bit limited. And I guess if experimentally, I mean, the whole field is looking for alternatives. It's a big effort. Modeling is a part of that, but it hasn't shown which replacements work the best. Yeah.
Okay, with that, let's thank Professor van der Waal again.